Okay, hello everyone. This is the cis256. Today we're going to continue to talk about recursion problems. And here's a very famous problem called Towers Hanoi. Let's take a look at what kind of problem that is. So basically, the problem is you have three poles, and in one of the poles, you have all kinds of disks from small to big, right? And it's ordered in order such that the biggest disk is on the bottom. Every disks above the top, the bottom one is slightly smaller, and so on and so forth. And the rule is you want to move all the disks from the leftmost pole to the rightmost pole. And the rule is at any time when you move, the smaller disk has to be on top of bigger disk. So in other words, you cannot have the smaller disk on one pole and then you put a bigger disk on top of a smaller one. That's not allowed. Other than that, you are free to do anything. So basically, you want to use with the help of the middle pole, and you want to eventually move everything to the right pole. So that's the problem. And only one ring at a time. Yeah, you can never put a bigger ring on top of a smaller ring. All right. So originally there were 64 rings of go to move. And every day the monk will move one step. And they said to move all 64 rings from the leftmost pole to the rightmost pole, it takes forever, like the whole age of universe to finish it. Is that really true? Well, how long is going to take? How many moves take for this for 64 disks to finish? Right, it takes a 2 to the power 64 minus 1, and then we'll let you prove that's a number. And if you only take a second to move, then it takes about 584.9 billion years, far more than the current age of the universe is known to human. All right. So how are we going to solve this recursively? We already told to give you some hint that we can use recursive thinking to solve this problem computatively. So what's the recursion part? Well, first of all, let's think about what's the base case, right? What's the base case? Obviously, if you have only one disk, it's simple. You just move from A to C and done. That's the base case, all right? Well, before you can move the last piece from A to C, you have to move the rest of the pile from A temporarily to B, which is called the intermediate pole. And you can use the final pole C as a helper to move everything to the B. Suppose you can do that. I don't know how you're going to do that, but suppose you can do that. Then you can move the last remaining disk to the final C, right? And then you can move the rest of the disk from the middle one, the intermediate pole, to the final pole using the original pole, the A. I will give you, does that make sense? So, yeah, that's pretty much the idea. Now, the beauty of the recursion is that don't think too complicated about this this smarter task, right? You may ask, how am I going to do that? Because you are actually doing this one step at a time, and every time you do the recursive call, you're supposed to get one closer to the truth. So don't worry. You just think about, this recursion would occur somehow magically. You would be able to do that, right? Because yeah, you may ask, oh, you have the disk A to the C, then you want to move everything from B back to A. Sorry, back to C using A as a media problem. So you actually convert that to a similar problem which has a smaller size. So that's all you need to know. Okay. So now let's check out some animations, see how they do it. Right. This is animation. So let's show how many pegs, 5 pegs. Oh, actually, cancel. Let me just do 3. 3 is easy. Let's say 5 disks. 3, let's show solution. As you can see, every time you move, the smaller disk is always on top of the bigger disk, right? So in each state, you are actually solving a smaller problem. And the 3-pose function, the from, to, and the middle one is actually interchanging every time you are in different state. As you can see, with 3-pose and 5 disks, there's already 31 steps, pretty big. All right, it's done. Not quite that we imagined. The middle one is the end, but nonetheless, these 3 are interchangeable. So let's see if we can actually code this. All right, let's see if we can actually code this. So how to code the tower Hanoi? So again, like we said, we're gonna define a function called move tower. All right. I'm gonna have a couple of first of all, the number of disks, okay, or height. So each disk is counted as 1, right? So like 3 disks height is 3, and so on and so forth. So that's height, and we're gonna do from, to, and width. Width means the median, right? Okay, that's just to avoid. Okay, so with 3 poles and a disk. All right. So first of all, if height is 0, then you're done, right? So if height is only if height is greater or equal to 1, then we can do this. First of all, we call the same function with height -1, because from with the median pole. Okay, so I'm gonna move everything but the last one from the beginning, the first one, to the middle one using the end one. Okay, and then I'm gonna move so I'm gonna move one disk. Okay, move disk from pole to, okay, so because from is just only one less from to the final disk, and then I'm gonna move everything from, because everything is in the with pole now, right? I'm gonna use the to pole, move to the from pole, so I move it back. So that's it, and then I'm gonna define a function called the move disk, which is just print out from to. So just print out move disk from, let's use the f string, like f string from 2. Okay, so from where? From FP to TP. Okay, very good. So that's that. I'm gonna call this move tower with 4 disks, and with 3 pole A, B, and C. All right, so let's run it. Let's run it. So you can see these are the answer: A to C, A to B, C to B. Finally, these are the steps involved. Okay, so don't worry too much about the middle steps, but just make sure you understand, the big picture. Okay, so let's just that's that tower handling. Okay, so next let's talk about a new topic, which is related to recursion, but oh. Okay, so it's related to recursion, but not really. So we're gonna do the coin problem. Minimum number of coins to make a change. So change problem. All right, so let's take a look what that problem is. So in computer science, there are many problems in computer science where you want to optimize some problems or values. For example, you want to find the shortest path between the 2-point map. Your GPS, software want to find the shortest path from A to B, or find the line fits best set of points. That's the 6 problems, and choose the fastest set of connections through a network, etc. These are all called optimization problems. We're going to talk about the whole optimization problem in a later week, but today we're going to deal with this one particular problem, which is called coin change problem. So you have some US coins, a quarter, a dime, a nickel, and a cent, right? So, with those combinations, it's actually a very clever design such that for the US coin system, all you need to do with, so the question is, with the US coin system, and give you a change like 68 cents, what's the minimum number of coins you can use to make a change? Well, the answer actually is actually if using, you can start with the biggest coin, like a quarter. If the number is divisible by quarter, not divisible, but if it's greater than a quarter, you can make it quarter first, and the remainder you can use the next smaller unit, like dime, and then that's nickel and cents. So if you do that, turns out that's the optimal solution, which we call the greedy algorithm, where you take the maximum face value coin first. That's greedy, right? So the answer is 6 in this question, 63. You can have 2 quarters, 1 nickel, 1 dime, 3 cents. All right. So again, like I said, this method of starting with the biggest coin value first, and going down to face value is called greedy algorithm approach. However, that only works for American coins, right? If there's a country that they have coins 10, 1, 5, 10, 25, and also a special 21-cent piece. Let's imagine there's 21 cents. So now, if I ask you the same question, if you use greedy algorithm, you will get 13, a wrong answer, right? So with greedy, you would pick the quarter and 21 cents and the dime. We'll have 3 cents left, and we would pick a nickel and 3 cents. So it's a lot, right? So 1, 2, 3, 4, 5 different coins. However, 21 is divisible by 63, so you only need the 3 21 cents to make the answer. So the answer is 3 instead of 5. So what's wrong with that? Well, you can actually think recursively. So this minimum change problem, basically, if you know, so for each step, right, you have some amount left. You want to try each possible coins. You just try them all, right? Try them all because there's no technique. You just try them all. So try 25 cents. How many minimum change if you subtract a 25 or subtract a 10? So if you subtract one, you use one coin, you just add one, right? This is the number of coins used, and the remaining face value you can plug into this same function again to see if I can calculate the remaining values for the minimum change, but then I'm adding one, or remaining values for 5 cents or 10 cents or quarter, remaining. So we just take the minimum of these 4 possibilities because for different face values, and that's the answer for that particular amount. Come again, so for the minimum change function, for any arbitrary amount, and if you have 4 different coins, right? You try them all by, okay, I'm using 1 cent or 1 nickel, 1 dime, or 1 quarter. And once you subtract that face value, the remaining amount you plug into the same function, calculate the minimum change. Don't worry how they calculate it, assume they give you the optimal solution. Use that solution, add 1. And compare this 4 different routes. You pick the minimum route. That's the best solution for your current amount. That's the idea. So here's some code. You can, first of all, set the minimum coins to be the change, which is like whatever cents. So cent is the most number of cents, right? Because the least value is 1 cent. And if you have 68 cents, then the 68 is your upper bound, in other words, right? So that's that. And then you want to reduce that upper bound. How? Well, if the change is exactly one of the face value of within the coin value list. The coin value list is a list of face value like nickel, dime, quarter, and cents. So if the change is within is one of them, then you're done. You only need one such value, such coin to make the change. So you're done. That's the one. One is minimum one, right? Suppose the change is greater than 0. Now, if not, okay, so here's one that you're gonna try all values. So I'm gonna try this comprehension. This is called list comprehension, where you have some coin value, C. And the C has to satisfy this if condition. The coin value have to be less or equal to change. Why? Because think about it, if your change is less than the coin, you cannot use that coin to make a change, right? That's simple like that. So the coin face value has to be smaller than your change. And if you can satisfy condition, you try all the coins in the coin list that satisfy this condition, and you can't just do this 1 plus minimum change thing, right? Change minus I is a remaining value we plug into this function to get the optimum solution, and you add 1 to 1 because you're using 1 face value, 1 coins from this list. And for each one, if this minimum coins is less than what's in your outer loop, right? Outer if else statement, then I'm picking the minimum one. Every time I get the value, I'm comparing the minimum one. So this minimum coin is really, the number of coins. If that's less than that, then use that to save it to minimum coins. Minimum coins also track the minimum value. So that's the technique to track all the minimum values. Finally, you determine the minimum coins, and you can test with that. Okay. Is this a good solution? No. Why? It turns out it's very slow. It takes over a minute to run, right? Because why is that? If you look at the cost stack, right, 26 cents, you try 1 cent, 5 cents, 10 cents, 25 cents, and you have this value left. And then 21, you have to call, subtract 1, you get 20, subtract 1, 19. But you can see there's a lot of overlapping, right? Here is 16 again, because you already compute this subtree, but you have to compute it again. And so does, I guess, 20, yeah. So there's a lot of redundancy here. So you end up with a lot of function calls that have same argument path. So you typically work over them. That's why it's so slow. Well, one thing that you can prove on this recursive answer is since you calculate the subtree 16, 15, 1, 6, you can memorize it. As well as you can cache the value. Every time you call the function with 16, oh, I already have that, then I can just reuse. I don't need to compute again recursively. That's called a memorization, right? Memorization is an optimization technique primarily to speed up the computational time by storing results of expensive function calls into some cache value. And when the same input comes, you don't need to go through the calculation again. You just directly do a lookup table and return the value, which is supposed to be faster. So here is the example of how caching works. So basically, in function A, input, if the input is already in the cache, then we can just do return the cache table lookup A. That's a dictionary in Python. So cache is a dictionary. In the dictionary, return the cache. Otherwise, you calculate the value, and don't forget the value you calculate has to be stored in the cache. The next time you call this function, you don't need to calculate again. The idea is each value, unique value, has to be calculated only once. And that's it. You don't do redundancy work. So that's the feature of memorization. So memorization actually helps. However, we have a better way, which is called dynamic programming. What is dynamic programming? So in recursion, we solve the problem from a top-down approach. In other words, we solve a big problem by solving a smaller problem first, and then graduate towards the base case and return, and hence solve the whole big picture. So top-down approach, right? Now, and as you know, there's a lot of redundancy recursive step because there's some overlapping problems. Dynamic programming, on the other hand, have a better solution to solve some of these problems, starting with a simple problem, like from the bottom, and you gradually build up the tables, and then you solve the bigger problem, which is the top. So that's how it works. Basically, you create a lookup table similar to the memorization doing a cache table, but instead of doing top down, but you're doing bottom up, basically. Right. So you start with basics. For example, here they have a table for solution for input as 1 cent, 2 cents, all the way to 11 cents. And you have these coins. So for 1 cent, because you only have 1 cent, there's only one step or one change. For 2 cents, two change, right? Because you have 1, 1, 3, 1, 1, 1, 4, 1, 1, 1. So 4 steps or 4 different changes. However, when you do a 5, because 5 exists in this, so you only have one coin 5. So it become 1 again. You get it? And then you just move on. So for any numbers, you will suppose that this table already have optimized solution for the previous answer. So like, for example, 6, you can look at 6 minus 5, which is 1. And then you add 1 coin 5. So there's 2 here. Or you can do 6 minus 1, and that's 5. And plus 1 is also 2, right? But the minimum is 2 here, and so on and so forth. So in other words, if you go all the way to 11, the answer is 1 on 10 because there is such a coin with face value 10. 11, then just add 1 to it, becomes 12. But you have to also consider the 5. So if you minus 5, becomes 6, and the answer is 2. You need the 2 coins to make a 6, and you add 1, so that's 3. And if you minus 10, you got all the way to 1, and so it's 1 plus the coin of face value 10, that's 2. So the minimum of that is 2. So there's 3 different conditions, and you just subtract each possibilities, and you look up the number in that table index and add 1 to yourself, and you get 1 to 1. So the minimum is 1. Okay, let's look at the code. Actually, let's code it ourselves. So dynamic programming. First of all, you already see the recursive solutions. So let's just go directly to the dynamic problem. So let's do a dynamic problem on the quant province, DP. So define DP make change, right? You have a coin value list, which is a list, and then you have a change, and then you have minimum coins, right? So the minimum value. So cents in range change plus 1 because we're starting from 1, right? So first of all, the answer start with cents because that's the maximum one, the upper bound. Okay, so now I'm going to minimize it. So again, for the index in a list comprehension, so I have a coin in coin values, value lists, sorry, value list. If C is less equal to what? Less equal to the cents. Okay, so we are building this. Yeah, build the DP table from bottom up. So from 0 to all the way to change, because the range function is it's not including the last value. That's why we need to change plus 1. Okay, so for that, for each j in that face value, if let's say minimum coins cents minus j, because j is the face value plus 1, right? You get that is less than coin count, then coin count is equal to that minimum coins of then minus j plus 1. So that's that. We can track the minimum value. If it's greater than, then we ignore, right? We don't try this. And don't forget that we're gonna update this table. This table minimum coins, minimum coins of this table is the coin count, the answer. So you try everything and get the minimum answer, and you finally return the last one, the table's last one, which is the change. Okay, so that's the whole thing. Let's try it. Amount equal to like 63 cents, and coin count. Let's start with all zeros, and in Python you just times amount plus 1, and then let's do DP make change. Let's say US coins 1, 5, 10, and 25, and amount coin. Okay. Count amount. Okay, so you call that function, and then let's try this table, right? Change for is coin count, change coin. So we're gonna just table print all these things. Actually, it's comma why I'm using this. All right. You can see for each values, you can print out all these minimum coins changed. So okay, so that's all for the dynamic programming. For now, we're gonna talk about more about greedy algorithm and DP coin dynamic programming later. All right, that's it. and have a good day. Bye.